Atoms are so small that they are hard to study directly. Therefore, atomic models are constructed to explain experimental data on collections of atoms. An early model of the atom called Dalton atomic theory in 1808 stated the following. First, all matter is composed of extremely small particles called atoms. Second, atoms of a given element are identical in size, mass, and other properties. Atoms of different elements differ in size, mass, and other properties. Third, atoms cannot be created or destroyed. Fourth, atoms of different elements combine in simple whole number ratios to form chemical compounds. However, with the developed technology in modern society, scientists found some mistakes in the original theory and made some changes to that. First, the early one stated that all atoms of an element are identical in size, mass, and other properties. However, mass spectrometry data proves that different isotopes of the same element exist. Plus, isotopes is defined as each of two or more forms of the same element that contain equal numbers of protons but different numbers of neutrons in their nuclei, and hence differ in relative atomic mass but not in chemical properties, in particular a radioactive form of an element. This means atoms of an element have the same number of protons but can vary in their neutrons, thus their properties and mass vary as well. Second, as Dalton said that atoms cannot be subdivided, created, or destroyed, the modern theory modifies that and states that atoms cannot be subdivided, created, or destroyed in ordinary chemical reactions, but these changes can occur in nuclear reactions. Law of definite proportions, or named as law of constant composition by Marcel Proust, states the following. First, the mass ratio, not mass, of element in a pure substance is always the same. Second, every pure substance has a fixed and definite composition. Third, a chemical compound always consists of the same elements combined together in the same proportion by weight. Dalton established the law of multiple proportions, which states that two elements can combine to form more than one compound. For example, carbon and oxygen can form both carbon monoxide, whose oxygen to carbon ratio is 1:1, and the carbon dioxide, whose oxygen is 2 times of carbon. Law of conservation of mass states that the total mass of substance present at the end of a chemical process is the same as the mass of substance present before the process took place. In 1897, J.J. Thomson used a cathode ray tube to deduce the presence of a negatively charged particle, which is electron. In this setup, cathode ray tubes pass electricity through a gas that is contained at a very low pressure. In 1909, Robert Millikan determines the mass of the electron using the oil drop apparatus. The mass of the electron is 9.109 times 10 to the negative 31 kilogram. Now let's get some conclusions from the study of electrons. First, cathode rays have identical properties regardless of the element used to produce them. All elements must contain identically charged electrons. Second, atoms are neutral, so there must be some positive particles in the atom to balance the negative charge of the electron. Third, electrons have so little mass that atoms must contain other particles account for most of the mass. Now, here comes the most delicious atomic model, Thomson's atomic model. As the picture shows, in this theory, the electrons are like plums embedded in a positively charged pudding. Thus, it was also called plum pudding model. Then here comes the Rutherford Guilfoyle experiment, in which alpha particles are helium nuclei and were fired at a thin sheet of a Guilfoyle. The particles hit on the detecting screen are recorded. The three main discoveries from the experiment are: first, since most of the alpha particles went through the Guilfoyle, Rutherford assumed that most of the atom is empty space. Second, some of the particles bounced right back since they hit a dense nucleus. Third, some of the particles were deflected because the nucleus has a positive charge. Then in 1919, Rutherford discovered protons and James Chadwick discovered neutrons in 1932. As is the case with all scientific models, any model of the atom is subjected to refinement and change in response to a new experimental results. In that sense, an atomic model is not regarded as an exact description of the atom, but rather a theoretical construct that fits a set of experimental data. Among subatomic particles, protons and electrons are the only particles that have a charge. Protons and neutrons have essentially the same mass. Meanwhile, the mass of an electron is so small that we can ignore it. The interaction of electromagnetic waves or light with matter is a powerful means to probe the structure of atoms and molecules and to measure their concentration. Chemists study how different forms of electromagnetic radiation interact with atoms and molecules. This interaction is known as spectroscopy. Just as there are various types of electromagnetic radiation, there are various types of electroscopy depending on the frequency of light we are using. For instance, UV-Vis spectroscopy, that is, when occurs within atoms and molecules when photons in the UV and visible ranges of the spectrum, wavelengths of about 10 to 700 nanometer, are absorbed or emitted.